Welcome to week 6 of machine learning for soil and crop management. This week's content was mostly based on theory. So, what I'll do is we'll go through some questions and their corresponding concepts or definitions so that we can cover theory in a more interactive way. Okay, so unlike programming where I just mono- monotonic speech. No, we will have an interaction with each other during this session. So, in this today's session, I have some previous year questions and some this week's question also, this year's question also. So it will be a combination. So for those of you who have not solved the assignment or maybe got some wrong answer in the assignment, uh, you can see where the answer was from or how to approach that. Okay, so let's start. So the first question, straight away from the definition itself, this question was taken. It's proximal soil sensors gather information about different soil properties by obtaining signals different with direct contact or from a distance within. So it's like it's asking that the soil sensors that were discussed in the session under the proximal soil sensor category, if we are not making the direct contact, then what is the range of the distance within which we will have a reliable reading from the sensor? So if we go to the definition of the proximal soil sensors, so it is said that it is ground based first of all, and used for determining the different soil properties, and we can have the measurements from either the direct contact or within a distance of 2 meters. So the answer will be 2 meters here. Okay, so two people have joined. So maybe from next time I'll ask you guys if you have your answers, and then we'll proceed. Okay, so let's look at this. What we will say classification, and we will have some questions based on this class. We'll have 2 3 questions based on this classification. So proximal soil sensors can be classified into 5 categories, as we can see here. One which measure reflected radiation, another one which measures incoming radiation, that is PXR, that was mostly discussed. And which another category which measures the backscatter electromagnetic waves or temporal propagation of electromagnetic waves, like how much time it takes for the electromagnetic waves to travel from the uh, transmitter to the receiver. Then the penetrometer measures the horizontal and vertical soil strength. And for the electrochemical properties like conductance and all, we have our ion selective electrode and ion sensitive field effect transistor. We also discussed about Nix Pro. As you, if you have seen the PPT, you will realize that it is about soil color, texture, moisture. We, in particular, in our lab, have this. We don't work in this field, but still, for some ground purpose, ground water analysis, we have this moisture content sensor in our lab. Yeah. So just look at it carefully. This Nix Pro DRS camera, we can it will measure the reflected radiation. Now the PXRF, the portable X-ray reflectance, the portable X-ray fluorescence spectroscope. So this will be measuring the incoming radiation from the soil. We'll see the working principle of PXRF, and then we have the backscatter from the electromagnetic waves that will be measured from electromagnetic induction, ground penetrating radar, time domain reflectometry, and frequency domain reflectometry. Okay, so if you are familiar with this, now let me ask some question. So the question is dash measures incoming radiation from soil. So the floor is open for answers now. Whether it is electromagnetic induction, penetrometer, gamma spectrometry, or ion selective electron. So you can type in the chat. Are you guys able to type? C. So Prachi has said C measures incoming radiation from soil. Let's see. Gamma spectrometry measures incoming radiation from soil. Correct. Now, what about electromagnetic induction? It measures the time of travel of electromagnetic waves or the backscatter of electromagnetic waves. Penetrometer, it measures the shear strength. You can say shear strength, but horizontal and vertical strength is what is written. And then iron, when iron comes, then we can rule out the other things, and we can just say the chemical properties or electrochemical properties. Okay, now we just now saw the answer of this question. Dash is used to measure the horizontal or vertical soil strength directly. So what will be the answer in this case? So funny thing, the option for this answer, okay, so no one is typing. No one is saying anything. I assume that it is too simple. Prachi is saying A. Okay, so oh yeah, no, it's not A, not B. Abhishek has said correctly. It is C. So we just saw this Nix Pro in the PPT. Also, we saw that it is for the color. PXRF was, yes, yeah, Prachi. So it is C because we saw that P penetrometer was the horizontal and vertical strength above. Ion is again electrochemical properties, and PXRS is the incoming radiation from the soil. Okay, good. So now I have kept this space empty for some reason. Yeah, let's see what is let's see some things about PXRF. So it is portable X-ray fluorescence, the full form, and then the method is called spectroscopy, and the instrument can be called spectroscope. We'll see about the working principle of PXRF for the subsequent questions, but for the coming question, I it is based on what are the advantages that we have when we use PXRF. So I will write some of the advantages, and let's see if you are able to answer the next question. So one advantage, it is portable. In the name itself we have mentioned portable, so we should write portable. Now there is no chemical reaction required. Okay, and then it is not non-destructive, and it can give multi-element analysis. So in the PPT, if you remember, there was 10 to 20 or 20 to 30 element analysis it can give at once. Sorry. Now look at these things carefully and let's see if we can answer the next question. So what are in out of these 4 points, which one do you think is not the property or the advantage of PXRF spectroscope? D, correct? Because it is saying that it is single element analysis, whereas we just saw that it is multi element analysis. Now my question is, okay, so I change it here itself. I should not have done that. So in in the PPT, this term, this non-chemical reaction, no chemical reaction required, is written as no consumables. So if that comes in one of the options, and probably that was in the option, and I changed it to this, so you should not get confused. It just means that it doesn't require any chemical reaction, and you don't need to have any kind of chemicals with you that will be used up after the analysis. That's why it is saying that not no consumables are required. Okay, and then this again a simple question: what are the advantages of portable X-ray fluorescence spectrometry? Okay, so I yeah, give this a shot. This is fairly simple only. I don't, okay, yeah, because this answer also was D, so I was not sure whether the answer is previous answer or this answer. So here also all of these, and no consumables again means the same thing, that no chemicals are required, because no chemical reaction is going to happen, and nothing is used up in this process. Okay, now let's see working of PXI. What is the working principle? Do we have, okay, I don't have another slide, so I'll have to adjust it here itself. So what are the components? Components are vacuum chamber, then cathode, then anode, which is made up of cooling system plus a metal target on which the electrons will be bombarded. The fourth is detector. So this all make up the portable X-ray fluorescence spectrometer. So what happens actually? So let me draw this. And what is the need of this? If you have gone through the PPT, you would have seen that nowhere was it mentioned that what actually is the need of this vacuum chamber. So does anyone know? Can anyone explain to me why do we need the vacuum chamber? If you are typing, you can type. If you want to say through mic, you can say. But if you are typing, then it will take some time. So better you raise your hand so that I know someone is actually typing. Otherwise, you can unmute and speak also. Okay. So if okay, so let me tell you what is the need of this vacuum chamber. See, what happens in the working principle of what is the working principle of this PXRF is, you have a vacuum chamber. I'll explain while going through the working principle. So we have a cathode and we put a high voltage through it, 20 to 60 kilowatt, I think it was mentioned. And when we do that, we excite the electron of this cathode to shoot out electrons are shooting out, and we direct it such that, so there's a very sophisticated alignment and all those things will be there inside the PXRF. This is just a simple representation. We excite it so that it will shoot electron beam, and that will be directed towards the anode or the metal, the target metal. Now if there is if there is air between these two, cathode and anode, then air is what? Air is nothing but oxygen, carbon dioxide, nitrogen, right? So if there is actually continue, if we have not sealed this and there is a continuous flow of air between these two, then some of these electrons are, instead of going and hitting to the anode, they will hit these atoms of oxygen, like molecules of oxygen, CO2, nitrogen, and other VOCs, and they will get excited. So it will decrease the efficiency of your PXR. That's why it is made sure that it is kept inside a vacuum chamber. And also sometimes what is done is there will be some noble gas that will be probably kept inside this chamber. I'm not sure whether it is done for PXRF, but in most of the cases when we need a non-reactive medium inside a fixed chamber, then we'll put noble gas inside that. But the basic principle is we want to have these electrons predominantly hitting this metal target, not the air between, and not get destroyed because of the air. Okay, so let me write whatever I said. So the cathode is supplied with high voltage, and electron beam is generated and directed towards the anode or metal. Okay, now what happens is, as the electron beam hits the anode with very high kinetic energy, it's not like they are going at like the car. Okay, so someone is, oh yeah, fine. So it's not like they are going at the speed of car 100 kilometers per hour. They are going at light speed. So when they are traveling at light speed, then they hit the anode, they have a enormous amount of kinetic energy. Even though their mass is very small, they still have an enormous amount of kinetic energy, and that kinetic energy is getting converted into heat when it hits the metal plate. So to keep the metal plate from melting, a cooling system is kept besides this metal plate that constitutes the whole anode. Now also, is in spite of this cooling system, metals with very high melting point are used in anode because of the high kinetic energy of the electrons that are hitting them. Okay, so now what happens when these high kinetic energy electrons are hitting these metal plates? There, the origin of the X-ray or primary X-ray, so to speak, occurs. So now, okay, let me use a different color. So from here, the primary X-ray is going to originate. And again, because of the sophisticated geometry, it will be directed to come out of certain space, certain dedicated space. And let's write this as primary X-ray. So it is coming out from this certain dedicated space, and now it is going to hit the subject that we want to analyze. And there is a detector near that object or material, which is going to detect the secondary X-ray waves that are originating from the material. So now, how this secondary X-ray waves are generated, and what is the name for the different type of secondary X-ray waves? So let's see. So primary X-ray waves are generated from anode. They pass through the filter and they come out and hit the object or the material. Now the detector detects the secondary X-ray. Now how does that happen? So when you have this primary X-ray wave hitting this object, what it will do is it will hit the electrons that are circling. So in this object we will have a center. So mostly these things are done for the atoms. They respond at an atomic level. So you have an atom with the nucleus. Inside that, neutron and proton are there, and then you have orbits of electrons revolving around that nucleus. So you have this, let's say, three electrons here, and then some here, and then some here. And these orbits are classified into, let's say, innermost is K, L, and M. So there is a classification system in class 12th and first year of BTech, first year undergraduate. We are taught of these systems. Nowadays, people are more inclined towards the S orbital, D orbital, F orbital, SPD, and F. But previously, this KLM was also more popular. So, what is hypothesized is that these X-ray, primary X-rays, sorry, I don't know how to go back in this. Keeps on erasing the things that I draw. So, what is hypothesized is that these X-rays are coming and they hit electron in the l- lowest orbit, that is the kth orbit. So, they hit the electron on this orbit, and this electron got excited, means it had a sudden bump in its energy, and then it flew off the atom. So it has created a disparity in the atom's equilibrium. So this X-ray primary, let's write primary as 1 degree. So primary X-ray hits the electron in the inner inner orbit, and correspondingly that electron in the inner orbit. So let me write electron gets energized and escapes the atom. Now, when it escapes, as I said, it is creating a disparity in the equilibrium of the inner orbit. So, what will happen? The electron from the outer orbit will try to come in and fill the empty space. Now, when the electron comes from the nth orbit towards this inner orbit, that is K, then we call it as K alpha emission. So when the electron from the L orbit comes to the inner orbit, the K orbit, it emits a certain kind of X-ray, that is the secondary X-ray, and we call that as K alpha emission when, so let me write it as L to K, and when the electron from the mth orbit, M orbit, comes to this K orbit and correspondingly emits another kind of X-ray, then it is called K beta emission. So when these electrons are actually jumping from here to this place, then they are emitting a secondary X-ray. That is what is getting detected by this detector. So that's why in this classification also we saw that PXRF, portable X-ray reflectance, sorry, X-ray fluorescence, measures the incoming radiation from the soil. Even though we only excited the soil to give the emission, still it measures the radiation incoming from the soil. So this is the atom in the soil where all this excitation of electron and secondary X-ray is getting emitted. So I hope this was understood. Now let's see if you can answer some questions based on this working principle. Okay, so the metal of anode in PXRF is usually selected among elements with what kind of melting point? High, very low, low, both A and C. Both A and C doesn't make sense, but yeah. So choose from these options and you can type your answer in the comment in the chat. A. So Prachi has answered correctly. It is A because the anode, the metal in the anode is getting hit by electrons with very high kinetic energy, and that is getting converted into heat. And because we don't want our metal to melt, we have a cooling system, and in spite of that, we also use a metal with high melting point. Very good. Now let's see another question. Which incident in PXRF does not relate to K alpha emission? So we know what happens in PXRF. Cathode gives the electron bomb. This electron beam hits the anode, creates primary X-ray that hits the electron in the K orbit, K shell orbit of this atom that we are doing the analysis of. And when it gets removed, then two things can happen. Either the electron from the L shell orbit will come to the K, or the electron from the M shell orbit will come to the K. And in one of these cases, K alpha emission occurs. So what do you think will be the answer of this? And the corresponding X-ray generated from this electron movement from the higher orbit to the lower orbit is the secondary uh, X-ray. That is what is detected by the detector. So which step among these written here is not involved in the K alpha emission? Abhishek has said D, very correct. Yes. So D, because K alpha emission occurs when the electron is moving from the Lth shell to the K shell, whereas K beta emission occurs when the movement is from M shell to K shell. So this is for K beta. Next. So let's see some more questions. So the wavelengths comprising the dash fluorescent X-ray radiation are identified and measured by a detector. So I have repeated this I think 2 to 3 times now. So basically this question is asking which X-ray is measured by the detector? Is it the X-ray that is generated from the anode, or is it the X-ray that is generated from the material? So this is a hint that I am giving with this line. B. Yes, both of you are correct. So the secondary X-ray that is emitted from the atoms of the material that we are analyzing, that are detected by the detector. There is nothing called tertiary and fused. Primary is the one that is generated from anode material. Very good. Okay, so now this question, this is something that I have not explained, but let's see if you guys can answer this question. So, which element present in soil or powder cannot be detected by PXRF scanning? So, basically, if you go to the working principle, you can hypothesize, or if you want to understand it more clearly, you can think like which element does not have which element is having so much strong bond with their electron that the primary X-ray that this anode or the anode creates is not able to excite that electron so that it is leaving the atom. Which element will have that so much strong? You can hypothesize that. It's not. I'm not saying that is the answer, but you can see like that might be the reason because of which this zirconium, because of which, yeah, we'll come to that, because of which this PXRF is not able to scan. It can be one of the reason that we cannot excite the electron. Another, that the radiation that is emitted by the electron movement from the higher shell to the lower shell is beyond the X-ray range. Either two, one of the two things can happen. Okay, so we can refer to the periodic table that was shared with us in the PPT. So see, PXRF are available for all these kind of elements, but not available for these. So what are the not available? Let's check the options. Antimony, the symbol for antimony is SB. So we can see SB is here. We have SB. Yes, Abhishek is correct. So it is lithium which is not available. What else is there? Rubidium, zirconium, all those are here. Zirconium is here. Rubidium is here. Right? The lithium is not available. So we can point out that lithium is the element which cannot be detected by PXRF as of now. Maybe in the future they will design some other kind of dampener or some instrument that will be able to detect the lithium. Okay, now let's see some other questions. Okay, so before that, we are now going to discuss about the soil. So Curtis, I am not able to pronounce his name. Let's write it as Curtis Marbuts. He gave a normal soil concept, and in that he classified soils into two major types. One which is having high uh, calcium carbonate (CaCO3), and the other one which is having high iron, so aluminum and iron. And he named them very cleverly Pedocalc and Padelphus. So if you have seen the PPT, you will or the presentation, you will realize that you will realize that this Cal here is for the calcium carbonate, and then Al and Fe is for aluminium and iron. Maybe he didn't mean to name that, but this is one of the tricks which you can use to remember. Pedocals is for high calcium carbonate, and pedal first is for high aluminium and iron. Now, it's not necessary, but since it was mentioned, see, pedocals are more abundant in western US, and pedal furs are abundant in eastern US. See, one more trick is to remember this is pedocals don't have E in their name, so you can say that they are in western US. Pedal furs have E in their name, so let's say they are west. We can see that they are from eastern US. I'm not saying that is something they thought of when they are naming. I'm saying that this is simply an observation which you can use to answer the following questions. So dash contains large amount of iron and aluminium. What will be the answer for this question? Is it pedicels, pedalfers, pedocept, pedoints? D. Nice. Simple question, and you have answered it correctly. Very good. What about this? Pedalfers. Wait a minute. Did I do a mistake? Oh yeah. Pedocals have E in their name. Yeah, it's my mistake. Maybe you cannot use that analysis. Pedalfers are mainly found in eastern US. Yeah, sorry about this. This was an oversight from my side. Yeah, maybe if you want to use threshold of 2e, then that is good. So it has 2e, so that's why it is in eastern US. Just some cheap tricks. If you can remember it, the better. Yeah, so pedal furs are found in eastern US. Okay, what do we have next? Now let's discuss about GAM, generalized additive models. So when we have all these, readings, sensor readings, we want to predict some soil properties with them. And see, linear regression is simple, but at the same time, linear regression is not able to capture the non-linear responses that are very often observed in the actual field. So, and see, the linear regression gives us the opportunities so that we can explain how the responses are coming. If something, let's say the linear regression of is represented as z is equal to beta naught x1 plus beta 1 x1 plus beta 2 x2 beta nx, and so if there are n plus 1 features, and we have fit a linear regression, so we will have n plus 1 constants. Now, based on the constants, we can say that, see, the z value is dependent on this feature more because the beta here is the highest. So we have a physical, we have explainability to the model. Whereas if we have non-linear model, then you have some x by y. Let's say if you have this kind of model, x1 square by x2 cube, and z is something like this. In that case, you don't have that much explaining power in this thing. See, if z is uh, when is z maximum? Either it can be low x or high x, low x1 or high x2. Sorry, when is z minimum? Low x1 or high z2? Or is there a ratio of x1 and x2 for which z is the maximum? So it creates kind of confusion when we are doing a nonlinear model. So there comes the generalized adaptive model, that is GAM. So what it does is it takes the information, or it takes the good goodness of the linear regression and then implements it into the non-linear regression. Why we use it? Because we cannot model non-linear features using linear model. You know? Okay, so we use this. What is this? It is how it is represented. Let's write that z is equal to s naught plus s1 x1 plus s2 x2. Maybe in the PPT it was a little bit confusing. That's why I am writing like this, sn xn. So what are these? This is not multiplication of s1 with x1. It is s1, which is a function of x. And what is the input argument? Only x1 value, x1 feature values are going to be the input of this. So it is like this. It is a function of x where the input is only x1. This s2 is a function of x, which is with the input only x2 values. So instead of having one complex equation, that is z is equal to x1 cube plus x or maybe x1 square into x2 cube divided by x4 root. So in this all the components are together mixed up, right? So instead of having this thing, what we do is we have functions of each variables, we fit functions of each variable separately. So this is a function for x1 variable, this is a function for x2 variable and xn variable, so on. So now we have n or maybe sometimes n plus 1 functions instead of constants. So this gives us the explaining power. So if we have this s1 value high, then we can say, see, now it is governed or it depends more on the feature x1, and that's why z is high. So we have some kind of we retain more of the explaining power compared to a simple or a conventional nonlinear expression. So that's why we use this gam, and also at the same time it provides a smooth nature. So if we that we will have when we are doing the conventional nonlinear fitting also, but that time we will not have the explaining power. So it is having the goodness of both, that it gives us the opportunity to explain our point, and at the same time it fits a nice smooth line to our data set, which the linear regression will not be able to fit. So we retain eye explaining power. Okay. So if you understand this, let's see if you can answer the next question. So generalized additive model GAM allows us to model dash data while maintaining explaining power. Discrete, nonlinear, linear, all of these. So what do you guys think should be the answer? B. Yes. Speaking uh, from the definition, B is correct. Thank you, Abhishek. Now here's my problem with this question. So when this question, the answer is correct, non-linear. But if you think about it, see the data that we are modeling, the data points, right? They are discrete data only. And is it necessary that our non-linear model, like if our function s1 x1 is simply beta 1 x1 and s2 x2 is beta 2 x2, can't we fit a linear? Can't we fit this? a GAM model to a linear model? We can do that, right? So this question, even though the answer B non-linear is correct, I feel like these two also should have been included. If you disagree with me, you can tell, you can say so. But what do you guys think now? The answer should be all of these or B only. See, because the data is always going to be discrete data. You will never get a continuous data from any sensor because all the sensors have a certain averaging period. Even if it is 1 second, there is a one microsecond where you will not have any reading, right? So all data is discrete, and we can fit actually. Yeah. So Abhishek agrees with me. Practically, D is also correct. If anyone is uh, thinking is has any other idea or the reason to justify that D is not correct, you can say so. Otherwise, we'll move forward. But for the assignment problem, simply if you are going to the definition and answering, then B is the correct answer. Okay. Now this is more of from the literature or from experience. Also, you can know there is not much explaining for this question, so you can go ahead and try to answer this question. C, nitrogen and carbon. Yeah, so dash and dash are two of the important elements for agronomic production and soil health assessment. Nitrogen and carbon. Correct. Okay, so what we have after this? So now we have some good part. Yeah. So before we go to these next questions, let me uh, do a worked out example, and then I want you guys to calculate the next questions without my help. So we'll use the table that was given to us in the PPT, where we had a reference classification, or we can call them observation. So and we had the model classification, and we classified the land as water, forest, urban. Water, forest, and urban. So this was the table. If you have the PPT, you can refer to it, or I'm going to draw it anyhow. We did the classification using the model, and they always we have to measure the accuracy. So we are making here the confusion matrix or the confusion table, and we will fill the entries. So there were 21 instances where it was actually water, and the model also told that it is water. There were 31 instances where the observation was forest and the model told it is forest. There were 22 instances when the observation was urban and the model also told that it is urban. Now, there were six instances when the model incorrectly classified the forest as water. There were zero instances when the model incorrectly classified the urban into water. There were five instances when the model incorrectly classified water as forest, and one instance where it incorrectly classified the urban as forest. And then same thing, 7 and 2. So you can see the 2 is for what, and so what do you think 2 represents? Can you write it in the comment, or you can say? You can speak, unmute your mic, and you can speak. What does 2 represent? What was it, and what was it classified into? So by the time you type it or you want to speak, I will write the total. So the total of these things will be written here. Total of these. So it is 37, I guess. And then 31. It is 33, 39, 23. And the total of the total, 95. So 95 total tests were done, total samples. Okay, so anyone, no one wrote anything in the chat. So let me just say 2 is for when the observation was it is forest and it was classified as urban. And 7 is for the observation of water. So actually it was water, but the model classified it as urban, land use, land cover, or something like that. Okay, so now that we have this confusion matrix, there can be three things that can be asked. That is, when we are restricting ourselves to these this week's content. Otherwise, there are many more things that can be asked based on the confusion matrix. So we can be asked producer's accuracy. Now here is something that you need to understand. Producer knows that my model classified, let's say, so observation of water was 33. So 33 water samples were taken. Out of it, it classified only 21 correctly. So that means producer knows that when it comes to the classification of water, my model's accuracy is 21 by 33. So what will it be? If you guys have calculator, you can take it out, because I am going to do the calculation in mobile. So if you can do it before me, we can save some time. So 21 by 33. We have 0.63. Okay. Now, can anyone tell me what is its producer's accuracy? So producer's accuracy, let me write it. It's the correct classification divided by total actual number in that class. So the correct classification divided by total actual number in that class, not total predicted number, total actual number. So now you guys tell me what is its prediction accuracy for forest. What should I put in the numerator and what should I put in the denominator? 31 by 39, exactly, correct. So Abhishek has written nicely, and it is, you are saying it is 0.79, correct. So I think you guys have the hang of it. Now let's move to the user's accuracy. User's accuracy is slightly different. Now, producer's accuracy is the accuracy, we can say that this instrument is able to classify Out of 33 times, it is able to classify 21 times correctly that it is water. Or out of 39 times, 31 times, it is able to correctly classify that it is forest. But when it comes to the user doesn't have this column, right? Sorry, user will not have this row, but user will have this row. So when we are saying user's accuracy, we mean to say the accuracy of the result presented by user. So when user says that out of my total 95, or out of all the times that I have classified the land use as water, I am true only 21 times. So let me write it here. Maybe it will be easily understood by this thing. Total classified in that class. So when we say user's accuracy for water, out of the 27 times the user has classified this soil patch or the area as water, only 21 times it is correct. So it will be somewhere 0.77. In the same way, what will it be for urban? No, no, no. Look at it carefully, Abhishek. Numerator is correct classification. So how many times urban has been classified correctly? Urban has been classified correctly 22 times. And how many times the model actually told that the area is urban area? 31 times, right? So it should be 22 by 31. You agree? Is that fine? Okay, good. Now that these two things are out of the way, the next thing is kappa coefficient. That was important, and I told you the way to calculate kappa coefficient in, I think, week 3 or something. So week 3 or week second. Now let's recall the kappa coefficient. So in that time, were only doing binary classification, whether patient has disease or doesn't have disease. But we have here multi-classification, multi-class classification. So in that case, how do we calculate kappa coefficient? It is simple. It is straightforward. Same concept will be used here as that time. So let me make it big little bit. We have kappa coefficient. It measures the accuracy of the model or the predictability of the model. So how it does the measurement is that it compares the accuracy two times, one of your model and one if the model was randomly by chance getting the answers correct. So the formula actually is simply P naught minus PE divided by 1 minus PE, where P naught is the accuracy of your model, total accuracy. Total accuracy. So If you guys remember the formula for total accuracy, can you tell me? Can you tell the total accuracy of this model? How many times it was correct out of 95 times? That is the total accuracy. See, even I have highlighted the times it was correct in red. Basically, the diagonal. So Abhishek has told 77. Let me calculate. So 21 times it was able to correctly classify water, plus 31 times it was able to correctly classify forest, plus 22 times it was able to correctly classify urban area, and total of 97 tests were done. So if we do the sum here, 21 plus 31 plus 22 divided by 95. So correct, 0.778 is the answer. Abhishek has said correctly. Now what is PE? PE is the probability that probability some of the probability that what is the accuracy when the model is saying that it is always water, plus what is the accuracy when the model is saying that it is always forest, plus what is the accuracy when the model is saying it is always urban. So by chance it is getting correct, in that case what is the probability? That is PE. So I need some space for this. What should I do? Is there an option to? Yeah, there is no option. Let me remove these things like examples, because these were fairly straightforward. We can use this space for the kappa. Let me make a boundary. Something is, if some space is required, we'll use the above space. Otherwise, we'll use this. So, what is the probability, or like what is the accuracy when what on when the model is saying only water? So, if you recall the last time how I told how to calculate this. So this is nothing but uh, number of times it was actually water. So let's write it as like this: actually water by total into predicted water by total. So I don't want to get into the nitty gritty of the probability here, but remember that these two events are conditionally dependent. That's why we have to multiply their probability to get the total probability of uh, this instrument or the prediction being correct when it is saying only water. So you can go back and freshen up a little bit. But simply to calculate this from this matrix, what we have to do is we have to look at the total number of times where the samples were actually water, meaning the observation total for the water column, and the total number of times the model said it is water, that is the sum of rho from the model side, and then we have to divide by the total sample for each. So you can write it as sum of observation for water plus sum of observation, so sum of classification for water divided by total sample size square. So can you tell me what is this p water? It is nothing but 33 into 27 divided by 95 square. And also tell me what is the P forest and P urban. I will tell you half of the answer. 95 square will be there in the denominator. What is in the numerator, you tell me. In the numerator, Abhishek is saying 39 to 27, correct? For urban, 23 into 31. Correct. Now let's simplify these things. So 33. So why don't we do this? P, since PE is going to be the sum of these. So why don't we take 95 square as common? Let me write it here. And we'll do the multiplication for only these two. No need to divide every time. Okay, so 33 into 27 plus 39 into 37 plus 23 into 31. So it is coming around 3047 divided by 95 square. The answer is 0.337. Check again. 0.337, yeah. So the probability that this model is giving the correct answer by chance comes to be 0.337. So what is the kappa coefficient now? We know P naught is 0.778. We know PE is 0.337. So what is the kappa coefficient? P is 778 minus 0.337 divided by 1 minus 0.337. So can you tell me the kappa coefficient? 0.441 divided by 0.0366. The kappa coefficient is 0.663. So I hope you now know how to calculate the kappa coefficient for any number of classes in the classification. One thing to note is that higher the kappa coefficient, the better. Higher is better. Okay, now let's see if we can answer the following questions. If correctly classified data for a site A is 15, correctly classified reference data for site A is 10, total reference data for site A is 30, total classified data for site A is 60, what would be the producer's accuracy for site A? Correctly classified data for site A is 15. Correctly classified reference data for site A is 10. Total reference data for site A is 30. Total classified data for site A is 60. So what is the producer's accuracy for site A? So if you are solving, then you can give a hands up, and then you can go with the answer. So D, Abhishek is saying D. So let me also calculate it. I hadn't calculated it, so let me just see. What is producer's accuracy? Producer's accuracy is nothing but correctly classify divided by total data for, no, sorry, total reference data, right? Total reference data. So we have correctly classified. So how it is coming as D? I'm not sure. Let me take a look at this. I should have looked at the assignments very carefully. Now that I read this question, it can be a little confusing. You have correctly classified. It is written as 15, and then correctly classified reference data as 10. So in that case, this correctly classified reference data should be taken as the numerator, right? So how did you get D, Abhishek? Why don't you tell us what is the numerator and what is the denominator?
So I have taken the numerator as correctly classified data and denominator as total classified data.
Mm, correctly, no. Total classified data.
Ah, yes, sir.
Oh,
Like
okay,
that I have
okay.
taken.
No, no, no. It is.
Yeah, yeah, it's wrong, I think.
Yeah. So it is. So the correct will be. See, when we are here doing for producer's accuracy, so
Mm.
it is for one element. So in that case, we have to see what is the correctly classified. So out of, yeah. Do you want to say something, Abhishek?
No, sir.
Oh, okay. So out of 20, out of 33 available for water, 21 was correctly classified. So this question may be a little confusing. We should take here correctly classified reference data. It doesn't make sense to write correctly classified data. But when you have this correctly classified reference data, you should ignore this thing, correctly classified data. So then you will have on the numerator as 10, and then total reference data for site A, that is 30. So it is 1 by 3 into 100 as 33.33%. This question was a little confusing, so if you didn't get it right, no issues. But the next question probably is little simpler than this and may be helpful to make good concept. Now, in an error matrix or that confusion matrix that you are writing here, if correctly classified sites is equal to 20, total classified sites is equal to 40, total reference sites is 25 for a classified class, then user's accuracy would be. So let's make that table. If we have correctly classified as 20, so let's say this is model, this is observation. and it is saying that total classified sites is 40. Total reference total classified sites is 40. Okay, so that is total classified sites. So here, so in this particular site, correctly classified were 20. But what it did was, let's say they were B, C, right? So it gave, let's say, 10 and 10 for this also. When it was B or C, in that case also 20 times it gave it as class A. So in that case, the total times it is classifying the site, it is saying that it is site A is 40. That is what is written here, and correctly classified is 20. But total reference sites for this particular site A, they were only 25. So let's say that two times it mistakenly told site A as B, and three times it mistakenly told site A as C. So in this case, now you tell me what is the user's accuracy. Remember that user's accuracy is correctly classified reference sites, if you want to add from the next last question. So it is correctly classified reference site divided by total classified in that site or in that class. So what will it be? Numerator and denominator. So numerator will be 20, correctly classified. Denominator will be total classified in that class. So as we have said, total classified in that class is 40. In that case, the accuracy will be 50%. Is that clear? So Abhishek, that 40 was the denominator, right? You didn't mean to say the answer for that. Okay, good. Good. Okay. So that is that for the error matrix or the confusion matrix. Now what do we have? Now we have, yeah, all the other things are based on theory. Let's see. Yeah. So this question. Now TXRF, when it is coupled with visible and near infrared diffuse reflectance spectroscopy to create a predictive algorithm for soil physical and chemical properties, then what kind of data does it take from the visible and near infrared diffuse reflectance spectroscopy? If you remember, in the last session or last to last session, we discussed about diffuse reflectance spectroscopy. So what kind of informations were we getting from that? These options themselves are very obvious if you look at it carefully. Yeah, correct. See, we are talking about diffused reflectance spectroscopy. So where we are getting the spectral data. In the name itself, we have that. Okay. Now, residual prediction deviation (RPD) is defined as, so in the PPT, if you remember, when Sir was discussing about the higher predictive power of the PXRF plus uh, visible to near infrared diffuse reflectance spectroscopy. They used this measurement, reduce residual prediction deviation, to gauge the higher accuracy of the combined model rather than the individual model. So how was it defined? This residual prediction deviation. If you don't remember, that is fine. It was just a small formula in the corner. But if you remember, you can give it a shot. Let's see. Okay, so residual prediction deviation is nothing but correct. Yeah, Abhishek is again correct. So it is RPD is nothing but standard deviation divided by RMSE, root mean square error. So sigma divided by RMSE. I don't think it is much important, but yeah. Okay, now we talk about NICS sensor. So NICS sensor, it was mentioned that it is used for color, texture, and some other things in the top, but mostly for the color. And color as a color sensor it is used. And what were some of its features? It was rechargeable and portable. Small diamond shape of sensor, it is portable. It has its own light source, right? It can connect to your smartphone. So for that, let me just write it here with Bluetooth. Then their apps is available again in the same, and it was small and lightweight. So these were some of the features of your NICS sensor. Now what happens is, due to it's alone, the NICS sensor was again not able to give very high accuracy. And so to avoid this human error, because in taking the reading or classifying the soil, and the error caused by the ambient condition, the error by human and ambient condition, to avoid the error caused by these things, what was done was they decided to shift the readings from this NICS value to a more generalized scale, and that scale was Munsell soil color. So it is nothing but a chart. It's a collection of chart that that gives the Munson soil number, or we can say Munson soil color number, based on the based on the matching of the cards with the color. So you have a bunch of cards with different color on them, and then you match the card with the soil color that you got, and then based on that you have a particular code associated with it, and you can use that code, or you can use that value in your predictive algorithm. So, what is this Munson soil color? So, it describes the soil based on three things. First is hue, second is value, third is chroma. What is hue? Hue tells us how red is the soil. Value tells us how dark is the soil. And chroma tells us how dull is the soil or how bright is the soil. See, you have to understand that darkness and brightness You cannot say that why we have this chroma and when we already have uh, this dark. Uh, the dark soil and the bright soil or the dull soil is different. How bright is the soil? Bright or dull? A little bit difference is there between this dark and dull. So this based on these three properties, long time back, Munson soil color chart was prepared. So you have cards of different colors, and you can match these cards with the color that you get, and you can use the numbers associated with them. As I said. Okay, so this is all I think we need to know about this sensor. Now let's see if we are able to answer some questions based on the information that I have given. So what are the features of NIX Pro color sensor? Out of these things, what are the features? Rechargeable? Yes. Own light source? Correct. Connect to smartphone via Bluetooth? Correct. So all these three were told there. Yes, Abhishek is said correctly. All of these are the features of NIX Pro color sensor. Okay. Now again, repetitive question. Which is not the reference for NIX Pro color sensor. So it has its own light source. It is rechargeable and portable. It connects with smartphone, but we have no idea about CCD detector. It doesn't even make sense. In nowhere in the throughout this week we heard about CCD. We saw a CCE, but not CCD. We can cross this out. This is the feature which is not present in the NIX Pro sensor, NIX Pro color sensor. Okay. Now, proximal sensors like dash can be used to measure real-time plant color description. Again, we just talked about that NIX Pro sensor is predominantly used for sensing colors. So in this case, proximal sensor, that is NIX Pro, yes, Abhishek is correct, is can be used to measure the real-time plant color description. Okay. Now the last question for today's session is Nix value can be converted to dash codes using Babel color conversion software. Now what do you think? A, correct. Because we just saw just now that to have a standardized thing, Nix color values or Nix values were converted to Munsell Munsell soil color number or Munsell soil color for having a proper ambient free and user error free classification. Still, users can cause error. That is not a question, but this is one of the ways to avoid or to reduce the chance of error. So somehow we managed to go through a session of whole theory. I forcefully added some of the examples. Kappa coefficient was not there in this. It was there, but it was not that deeply discussed. But still, I wanted to share with you guys how to calculate it in multi-class classification. Yeah, I think that's all for this week. If you have some questions, you can ask me. And if there was discrepancy in the answer in the assignment, then you can also inform, and I will pass the message on. So yeah, Prachi, I think you asked me a question about whether the exam will be objective or subjective. I have mailed them. I have not yet received a response. So when I receive it, I'll pass on to you.
Sir, can I ask a question?
Yeah, yeah.
Sir, you have told the kappa coefficient more the kappa coefficient more will be the accuracy like that you have told.
No, actually, I meant to say that when kappa coefficient is more, then you can be sure that your model is actually predicting the trend. It's not by chance that model
Mm.
is correct. It's not like 100% related to the accuracy of the model.
Okay, okay, sir.
Yeah, but it's like the model is predicting something. It's trying to capture something.
Okay, okay, sir. That range, what is the range of that higher kappa coefficient, sir?
See, okay, so let's see here. Let's try to. I am also not sure about the range, but let's try to figure out the range from the probability.
Sure, sir.
So, if it is more than one, then it can be anything, right? So let's see if it can be more than one. So if your p, let me use a fresh slide. Yeah. So kappa coefficient is p naught minus p, 1 minus p. Let's see if it can be more than one. So p naught minus p, 1 minus 1 minus p. So this will get cancelled. Pe, and we have p naught greater than 2 times pe. So can the total probability, or what you can say, total accurate probability, what was the term? Uh, Total accuracy of the model. Can the total accuracy of the model be greater than 2 times of the probability by chance? Yes, it can be greater than 2 times. So if kappa coefficient can be greater than 1 also. Or let me just uh, Google it to confirm. I don't want to say wrong things. But based on this proof, we can say, oh, okay, it seems that I was not correct here. Kappa coefficient range varies from -1 to -1. So it seems that the total accuracy of the model cannot be greater than 2 times the accuracy of when the model is just purely by chance. Okay, so my bad. The range of kappa coefficient is -1 to 1, and this point more than zero point 0.4 or zero point 0.6 is good, fairly good. The range between zero
Thank you,
point
sir.
0.4 to zero point 0.6 is fairly good. Our is more than zero point 0.6, so our model is, we can consider, not our model, the model that was shared in the paper, it is good model.
Thank you, sir.
Yeah. Okay.
Sir, another question.
Yeah.
It's a general one. Actually, if we are going to develop a predictive model of anything like soil properties, like organic carbon or any soil properties, how much time it will take, sir, or how many factors you can include?
How many factors? I'm not entirely sure, because first, I have to confess that this is not my area of expertise, and second, it based on the papers in my field. If I
Yes, sir.
explain my field papers, so it all depends on what kind of predictions you want to make.
Okay, sir.
So, like, see, in case of one of the papers that was discussed in the PPT, it was shown that organic content can be estimated just based on color itself.
Yes,
Based,
yes, sir.
yeah, but in some cases they showed that if you have the nix plus the spectral, then it is more accurate. Some cases they showed that if you have the PXRF plus the spectral, it is better. So it depends on what kind of predictions we want to make.
Okay, okay, sir. Thank you, sir.
Okay, thank you. Thank you. So does anyone else have any question? Because I will also learn from the questions as I learned from the kappa coefficient. Okay, so if no questions are there, then we'll wrap this up.